Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical. In this particular presentation, I will be talking about the recovery and recrystallization. These are the two fundamental aspects related with the cold working and hot working, about which I have talked in the previous lecture. When the cold working is done, the metals with the good work hardening tendency tends to get hardened rapidly, increases the yield strength, reduces the ductility and makes the deformation difficult. And continuous deformation can make the materials sensitive for cracking. Therefore, it becomes important to induce some ductility and to soften the material. And for that softening, in process annealing is carried out, which induces the softness, and that softness comes from the recovery. Okay. So, that is one of the fundamental aspects related to the cold working. Similarly, when the metal is worked at a high temperature like hot working is carried out, then the deformation coupled with the high temperature causes not just recovery, but also the recrystallization. So, when the deformation beyond a certain limit is carried out, then at a high temperature the deformed grains vanish and the new grains reappear through the recrystallization. So, what are the various mechanisms related with the recovery and the recrystallizations, various factors affecting these two aspects along with the grain growth? About these I will be talking in this presentation. So, this broadly content recovery and dynamic recovery. The recovery is one which happens when the deformed metal is heated to the high temperature, and the dynamic recovery is one when the metal is heated at high temperature, at the same time it is deformed plastically. So, what are the effects of the recovery and recrystallization and dynamic recrystallization, and effect of recovery, recrystallization and grain growth on the properties of the material. So, let us say when we start with any material, initially you see the metal like this may be in annealed condition, means there is no dislocation, material is in most soft condition, no dislocations. But when the material is subjected to the plastic deformation, then lots of dislocations are induced, they are developed, and that leads to the work hardening when the deformation is done under the room temperature or low temperature conditions. So, initially in the work hardened condition, lot of dislocations are induced. These dislocations increase the strength, hardness, but at the cost of the ductility of the metal. Okay. If this deformed material, if heated to the high temperature, say 0.1 times of its melting point or more, then these dislocations tend to annihilate, and annihilation means the loss of dislocations from the deformed metal will be occurring, and this loss of dislocations reduces the hardness, reduces the strength and increases the ductility. So, a deformed metal when subjected to the heating, recovery is the first thing that will be happening. Okay. If that heating is done further at a higher temperature in the range of say 0.3 to 0.6 times of its melting point, depending upon the kind of metal, then we will see that after the recovery the metal tends to show the partial recrystallization, where the new grains start forming at the selected few locations, especially at the grain boundaries. So, this is the case of the partial recrystallization, when the few new grains will start forming, and then if the high temperature is maintained for further longer time at which recrystallization is taking place, then we will find the fresh new grains which are free from any strain, free from any crystallographic defect. Thereafter, if further high temperature is maintained for further longer time, then the grains can grow in two ways. One is the grain, all the grains grow in, and the obviously the smaller grains are consumed by the bigger grains, but the grain is largely of across the section, the coarsening of the grains will be taking place. So, that is the normal grain growth, where the change in grain size from one small size to the larger size take place. Then we will see in the select cases the deformed materials show the abnormal grain growth, where one or few grains grow abruptly significantly as compared to the other grains, and that becomes the case of the abnormal grain growth. So, this is what happens when the an annealed metal is subjected to the deformation. Dislocations are produced causing the increase in strength and hardness of the material, but at the cost of ductility. Then higher temperature will be causing the recovery at lower temperature exposures. Further higher temperature exposure will be causing the partial recrystallization, then complete recrystallization, and then grain growth. Okay. So, this is how the things will be happening in all these cases. You see, the highest strength and hardness will be offered by the material in the deformed conditions, work hardened condition, but thereafter continuous decrease in the strength and hardness will be observed after the recovery, then further reduction in yield strength and hardness after the recrystallization, and then further decrease in strength and hardness after the grain growth. But in all these cases, when these drop in strength and hardness is taking place, this will be causing the increase in ductility. Okay. These things will be coupled with the increase in ductility. So, we will try to see the mechanisms and various factors associated with the recovery, recrystallization, and the grain growth in this presentation. So, recovery and work hardening, you know that when a plastic material is deformed plastically at room temperature, it induces lot of dislocations, and when the number of dislocations are increased, the movement of dislocations becomes very difficult because of interfering effect of these dislocations with each other. So, increased dislocations density increases the strength and hardness because of difficulty in movement of the dislocations and the requirement of the higher stress to cause the dislocation movement. So, because higher density dislocations cause more interference in movement of dislocations, resulting in the higher stress requirement to cause the deformation. While at the higher temperature, the atomic movement and rearrangement of these dislocations take place, and therefore, these dislocations annihilate, these vanish, the number of these dislocations reduce. So, reduced dislocation density in turn makes the dislocation movement or the deformation easier or even at the lower level of stresses, and that in turn results in the softening. Means when the dislocation density is reduced, when a deformed metal is heated to the high temperature, that will be making this deformation easier due to the reduced stress requirement to cause the dislocation movement and facilitate the deformation. This is observed in form of the metal softening. So, loss of dislocation at a higher temperature is basically called recovery. Okay. At what temperature recovery takes place? It has been observed that temperature around 0.1 times of its melting point is needed for the recovery to take place. So, minimum temperature required for recovery in a metal after the deformation is around 0.1 times of its melting point on absolute scale. So, this is about the recovery. Okay. But if we talk of the recrystallization, for the recrystallization we need a greater temperature like 0.3 times of its melting point for pure metals, while for alloys say it is from 0.4 to 0.6 for the alloys. So, if we can see here, the alloys need higher temperature for recrystallization to take place. So, if we see this, recovery will be happening at a lower temperature than the recrystallization. So, if the deformation is taking place only at a very low temperature, then it is possible that the deformation effect will be reduced somewhat by recovery, but still the grains will remain deformed. They will have a lot of crystallographic defects, and no new grains may be formed if there is no recrystallization happening due to the lower temperature. So, say if the temperature is less than for pure metals 0.3 times of its melting point and the material is subjected to the deformation, only recovery can take place. So, that will be causing the partial drop in the yield strength, little drop in yield strength and hardness, but if the recrystallization is happening, then it will be causing the significant drop in strength and the hardness. So, this recovery process is often referred as the stress relief annealing in practical applications. As far as the factors affecting the recovery is concerned, there are numerous factors. So, few important factors are like how much strain has been induced by the deformation. Okay. So, greater the strain induced, greater will be the resistance to the recovery. Recovery will be slow because of increased number of dislocations, increased dislocation density, increased interlocking and network of the dislocations. Higher the temperature, easier will be the recovery, greater is the purity, easier will be the recovery, finer is the grain size, easier will be the recovery, higher is the stacking fault energy, easier will be the recovery, and absence of second phase particles, easier will be the recovery, lower is the strain rate, easier will be the recovery, and the deformation temperature is high, there may not be any requirement of the recovery because it will be causing the dynamic recrystallization itself when a recovery is happening. Dynamic recovery may be happening. Okay. The complexity of the deformation means if very complex deformation is taking place, then that will make the recovery difficult and complex. So, these factors in turn affect the degree of, you see, whenever the deformation is carried out under the variety of conditions of the material, grain size, the stacking fault energy, the kind of the constituents which are there, deformation temperature and complexity of deformation, these factors in turn affect the degree of stored energy due to the deformation, and which in turn determines how the recovery will be happening in the material. So, this is about little in detail of the factors affecting the recovery as far as the temperature of at which has been used for a recovery. As the annealing temperature increases, the rate of atomic diffusion rises, facilitating the movement and annihilation of the dislocations, thus promoting the recovery. So, higher the temperature, faster will be the recovery. Impurities hinder the dislocation movement, slowing down the recovery process. So, alloys will need higher temperature for a recovery, and if the for at a given temperature, if the metal is pure, recovery will be faster as compared to that of the alloys. The grain size, smaller the grain size typically leads to the faster recovery because due to the larger grain boundary area presence in case of the fine grain size materials where dislocation movements are easier to facilitate the recovery to happen. Then the deformation induced strain, greater is the deformation, greater is the strain induced. So, that will be causing the increased density of the dislocations that in turn will be resulting in the slower recovery of the metal. Other factors like the metal with the higher stacking fault energy, they will be recovering fast as compared to that of the low stacking fault energy because of the easy movement and gliding of the dislocations and their rearrangement in the high stacking fault energy metals. Second phase particles, as I have said, the presence of precipitates impede the dislocation movement and thereby hindering the recovery. Strain rate, higher the strain rate generally lead to the denser dislocation network resulting in the slower recovery, and the deformation temperature, if the deformation is being undertaken at a higher temperature, then the recovery will be happening at the time when the deformation is taking place itself, and therefore, dynamic recovery will be effective, and it is possible that a static recovery means the reheating means heating of the deformed material may not be needed. Okay. So, the deformation of metal at high temperature promotes the dynamic recovery, reducing the need of the post deformation static recovery requirement. So, obviously, we have to reheat the deformed metal for the recovery at lower temperatures, but if the deformation is being carried out at a higher temperature, then the dynamic recovery will be happening, means when the recovery will be happening when the metal is being deformed itself. Okay. And so, it may not require later on any kind of the separate treatment for the recovery of the deformed metal. Okay. Then complexity of deformation, a complex deformation patterns where large shear strain can create more entangled dislocation density and making the recovery more difficult. Okay. So, the complex deformation makes the recovery difficult because of the complex network and network of the dislocations. So, what is the dynamic recovery? Static recovery is one which happens when the metal is heated after the plastic deformation. Okay. A dynamic recovery is also a kind of recovery process, but it happens during the deformation itself, which is happening at a higher temperature. So, dynamic recovery is a recovery process happening during the deformation under the conditions of high temperature and strain. So, a metal which has been deformed under the cold conditions having the work hardening effect subjected to the heat treatment later. So, this heating is done for recovery to take place. So, this is called static recovery, we can say. But when the deformation is undertaken at a high temperature, So, heating coupled with the deformation, if this is the combination, then the recovery will be happening even when the deformation is going on. So, this is called the dynamic recovery. Dynamic recovery will be happening during the deformation itself. Okay. So, the dynamic signifies that recovery is happening in the real time as a material is subjected to the plastic deformation. Okay. And now, annihilation of the dislocations during the deformation at a high temperature is called dynamic recovery, and dynamic recovery neutralizes the effect of work hardening and resulting in the flat stress strain curve. So, usually what we find, like stress strain curve becomes somewhat like this. So, what it indicates, increasing stress requirement to cause the further strain or the plastic deformation. So, this is what happens in the cold condition, but if the metal is subjected to the deformation at a higher temperature, then initially it is fine, then it will become flat. So, initially work hardening effect is dominating over the recovery. After reaching a critical strain value, the recovery will be happening fast and it will be balancing. The softening will be balanced by the hardening which is taking place. So, this is the case where work hardening effect will be balanced by the dynamic recovery. So, that is called DRV. It is this is how it is expressed. So, work hardening effect is balanced by the DRV, and that makes the flat stress strain. So, this flat stress strain curve is a typical sign of the dynamic recovery, where dynamic recovery is neutralizing the effect of the work hardening. If the dynamic recovery is not really very effective, in that case we may find the decreasing effect of the work hardening. So, earlier it was happening like this, still work hardening is taking place, but the rate of the increase in the stress requirement to cause the further deformation, that will be reduced. So, it may not be flat, but it may, the extent of softening is such that still it requires the increased level of the stress. So, the work hardening is not exactly balancing the DRV, but still work hardening is dominating. If it is balancing, then this curve will become flat. Okay, so this is what we can see from this curve, the stress, strain, and here initially the no dislocations, then due to the deformation dislocations are induced, and then subgrains are formed, and then at a high temperature when the dynamic recovery will start here and it will become flat. But you will see in case of the dynamic recovery, no new grains are formed. Whatever the grains are there, in those grains the dislocations will be induced and they will be annihilated. The new grains are not formed. New grains are formed only in case of the recrystallization. So, if we compare the recovery and dynamic recovery, then you will see in terms of the timing, recovery or static recovery happens after the deformation when the metal is subjected to the heat treatment, while the dynamic recovery happens during the deformation itself. Okay, that happens at high temperature. So, application recovery is used in case of cold working to induce the ductility of partially processed metal, and dynamic recovery is often seen in process like hot working involving the deformation at a high temperature, and this involves this causes the simultaneous strain relief and avoids the work hardening effect. Now, this is the summary of the entire thing that I will be talking in this presentation. So, here we are starting the deformed metal with the lot of dislocations. When it is heated to the high temperature, what will be having the recovery, number of dislocations are reduced. Then further higher temperature means if the further higher temperature is maintained for longer time, then the new grains will start forming, that will be leading to the partial crystallized situation. And then when the recrystallization completes for at a higher temperature for further longer time, fully crystallized grains will be forming. These will be crystallographic defect free, these will be new grains and these will be completely different from what it was earlier. Okay. And then further, if the high temperature is maintained for further longer time, then the grain growth will occur. So, what will happen to the metal when the high temperature is maintained for a longer time? Initially, there is a minor drop in the strength and hardness in the recovery phase. This is the recovery phase. But when the recrystallization starts, the drop is very fast. Okay, in the strength and hardness. Okay, and then when the grain growth takes place, again in the grain, in case of the grain growth stage, we will see that the drop in strength and hardness is little slower. On the other hand, ductility is enhanced with the in recovery, recrystallization and grain growth. So, this is what we can understand as far as the compiled the diagram is with regard to the hardness. Initially in the recovery phase, there is a very marginal drop in the hardness. The grains are still in the deformed condition, no new grains are formed, and the strain is relieved, the crystallographic free grains are formed. This will be causing the huge drop in the hardness. During the recrystallization phase, new grains will be formed and then grain growth will be happening. Okay. So, this is the temperature zone for the recovery, then this is the band for the recrystallization, okay, and then grain growth. Okay. So, this is how it will be showing that there will be continuous drop in the hardness and strength during the recovery, recrystallization and grain growth. So, on the other hand, there will be continuous increase in the ductility, which will be improving the ability of the material to get deformed, okay, without cracking. Now, we will talk the things about the recrystallization. Recrystallization is the process by which the new grains are formed, and these grains, when new grains will be formed, they will be completely different set of the grains which are free from strain, free from any crystallographic defects. Okay. So, the deformed grains will be resulting in the new grains during the recrystallization, which are free from any crystallographic defect, and this occurs through the mechanism of the nucleation followed by growth. So, at the grain boundary area, new grains will nucleate as we have seen in the previous slide, and then these grains will be growing later on, consuming all work hardened grains. Okay. So, the recrystallization occurs through the nucleation mainly at the grain boundary, followed by growth of until the original grains are entirely consumed. Original means work hardened grains are completely consumed. Recrystallization is usually accompanied by, so this is coupled with the reduction in strength and hardness and increase in the ductility. That is about the effect of the recrystallization of the work hardened metal. So, the process may be induced deliberately to reduce the strain hardening effect in and embrittlement. So, it is possible that when the material loses its the ductility, and if you want to work it further by the cold forming based process, then the recrystallization is induced. This kind of step is induced in the process, so that the ductility can be induced and material can be worked further. It is used for softening the metal which has been previously hardened or embrittled by the cold working, and control the grain structure of the final product as per the requirement of the properties. As I have said, the factors that affect and how it affect the recrystallization temperature and how the recrystallization affects the material aspects. So, you can see the recrystallization temperature, typically recrystallization temperature is around 0.3 to 0.4 times for the pure metals of its melting point in Kelvin scale, and the 0.5 to 0.6 times of melting point for the Ly. So, during the recrystallization, lattice defect free crystal lattice defects are repaired. So, the fresh grains without any crystallographic defects are produced. New crystals form through the grain growth and the nucleation and grain growth mechanism, and this process reduces the dislocation, which in turn decreases the strength and ductility, while decreases the strength and hardness while increasing the ductility. This is just for an example, because recrystallization temperature is found over a range like say 110, say 230. Just for an example, I am writing this 220, say 400, okay, 550 and 1100. Just for example, I am writing these values. Why? Because the temperature at which recrystallization will be occurring, that will not be fixed, but it will be affected by lot of things like composition, microstructure, grain size, work hardened conditions, time, etc. Just for an example, I am showing this, like the different metals show the different value of recrystallization temperature, but it is not one value, it is a range actually over which this will be happening depending upon the multiple factors. So, as we can see, alloys show higher recrystallization temperature than the pure metal, then increasing amount of the cold work decreases the recrystallization temperature. The amount of work being done, plastic deformation being done in a metal, then decreases the recrystallization temperature. Finer grain size in cold worked metal decrease the recrystallization temperature, and increasing the annealing time decreases the recrystallization temperature. So, the composition, the grain size, the extent of the deformation which has been induced, and the metal is having the stored strain energy stored in the metal. So, these factors affect the recrystallization temperature. Likewise, annealing time, increasing annealing time decreases the recrystallization temperature. So, we can see if there are certain phase, if metal is not pure, there are alloys, there are certain phases, there are certain particles or reinforcing agent, then these particles and the phases or precipitates, all these will be resisting the recrystallization. So, recrystallization is prevented or significantly slowed by alloying elements, dispersion of the small, fine and closely spaced particles due to the Jenner pinning effect. So, presence of these alloying elements, phases, particles, precipitates actually adversely affects the recrystallization process. It is slowed down. So, this directly opposes the driving force arising from the dislocation density for recrystallization and will influence the both nucleation and the growth kinetics. Now, depending upon the condition when the recrystallization is happening and the way by which it is happening, there are various types of recrystallization. One is say static recrystallization. So, deformed metal is exposed to the higher temperature, then the new grains are formed after the deformation. Material has been deformed and it is subjected to the heating after the deformation. Then formation of new grains will be leading to the recrystallization, and this kind of thing is termed as static recrystallization. But when the deformation is done at a higher temperature, the recrystallization will be happening there itself in the real time basis, and that will be termed as the dynamic recrystallization. So, recrystallization may occur during or after the deformation. When the recrystallization is happening during the deformation, it is termed as dynamic recrystallization, while when the recrystallization which is happening during the subsequent heat treatment after the deformation, then it is termed as static recrystallization. And then continuous and discontinuous recrystallization is another type. So, recrystallization may occur in continuous or discontinuous manner. When it occurs in discontinuous manner, then in this case distinct new grains form and grow, while in case of the continuous recrystallization, where microstructure gradually evolves into the recrystallized structure slowly and more uniform, new grains are formed. Okay. The secondary recrystallization occurs when certain very small number of grains grow selectively at the expense of many other primary recrystallized grains, and this causes the abnormal grain growth. This can be very detrimental to the material properties. Okay, little bit more about the continuous and discontinuous recrystallization. So, as far as the structural evolution is concerned, in continuous recrystallization, new grains form through the gradual transformation of the existing subgrains, while discontinuous recrystallization, in case of the discontinuous recrystallization, new grains nucleate at specific locations like grain boundaries and then grow independently. As far as the microstructural evolution is concerned, continuous recrystallization shows a more homogeneous change in the microstructure as deformed materials grow gradually and transform into the recrystallized grains, whereas discontinuous recrystallization results in the more distinct appearance of the clearly separated new grains. Okay. Then a strain dependence, as far as the strain dependence on the continuous or discontinuous recrystallization is concerned, the continuous recrystallization will be happening when the strain rate is high, where the subgrain boundaries can easily evolve into the high angle grain boundaries, while the discontinuous recrystallization may occur at the lower strains with the nucleation at the pre-existing grain boundaries. Now, factors affecting the recrystallization, they are basically the two factors that are important. One is the temperature and another is the deformation. Material must be deformed to a critical level for to trigger the nucleation and formation of the new grains. Okay, and there must be some minimum temperature for recrystallization to happen. So, annealing temperature exponentially affect the nucleation and growth of the recrystallized grains. The critical recrystallization temperature decreases with the annealing time, and prior critical deformation must be applied to the material so that nucleation can start and sufficient stored energy can be created to drive their growth. So, critical deformation of the material is one requirement, and then minimum recrystallization temperature. Minimum temperature must be attained, and this minimum temperature decreases with the increase of the annealing time. That is another aspect. Various factors affecting the recrystallization temperature. So, there are many other things also, like higher is the amount of deformation or lower is the deformation temperature. These are the two aspects. Greater is the amount of deformation and lower is the deformation temperature, means hot deformation is being carried out to the greater level at lower temperatures. Increasing the prior deformation or reducing the deformation temperature will increase the stored energy, and that will increase the number of potential nuclei that will be produced, and this in turn result in the recrystallization temperature will decrease with the increasing deformation. Nucleation and grain growth. So, increasing deformation or reducing the deformation temperature increases the rate of nucleation more than the growth rate. So, this is very good situation where nucleation rate is being increased, as that increase in nucleation rate is much higher than the growth rate. Okay. So, that in turn results the fine grain size, and that will be happening when the extent of the deformation is increased or the deformation is being done at lower temperatures. Grain size. So, increasing grain size increases the recrystallization temperature as some grain boundaries, as grain boundaries are good site for nuclei to form. Increasing grain size results in the fewer grain boundaries, which in turn decreases the nucleation rate and hence increases the recrystallization temperature. The driving force for recrystallization is basically strain energy is stored. When a metal is deformed plastically, we do lot of work, and part of the work is converted into heat and very little fraction is retained in the material in form of the strain energy is stored. Okay. So, that is around the 1 to 5%. Okay. So, the plastic deformation of the during the plastic deformation work is performed in the metal, majority of this work is converted into the heat and some fraction is retained in the metal as a defect or the dislocations in form of the strain energy stored. So, the driving force for the difference in energy between the deformed and the recrystallized state, that determines the driving force and how easily there will be recrystallization. Greater is the driving force, means greater is the strain energy stored, easier will be the recrystallization. Now, the dynamic recrystallization. So, dynamic recrystallization is also kind of recrystallization which will be happening at a higher temperature. Okay. So, the dynamic recrystallization is a type of recrystallization. The dynamic recrystallization, as opposed to the static recrystallization, the nucleation and growth of the new grains occur during the deformation itself rather than afterward as a part of the separate heat treatment. So, a static recrystallization is one which will be happening during the heat treatment after the plastic deformation, but the dynamic recrystallization will be happening when the deformation is carried out at a higher temperature. So, this curve shows three different situations when only the work hardening is being done. So, there is no recovery and recrystallization, there is a continuous increase in the stress requirement to cause the plastic deformation. There is no softening. But when the deformation is carried out at a higher temperature and the dynamic recovery is prevailing, then the dynamic recovery will start balancing the work hardening effect after a certain stage. Initially, it is fine, there is increasing stress requirement to cause a further strain, but after reaching a critical stress or a strain value, the dynamic recovery becomes active and that balances the work hardening effect is balanced by the dynamic recovery. Okay, and therefore, this curve becomes flat. And the third stage is where the work hardening effect is there is in the beginning, then the recovery comes into, and then recrystallization comes into. So, the work hardening plus dynamic recovery plus dynamic recrystallization. So, when the dynamic recrystallization comes in, this causes significant softening of the metal and that in turn deviates the curve significantly. So, these are three curves indicating the presence of three different the kind of the metallurgical aspects: work hardening only, work hardening plus dynamic recovery, and work hardening, dynamic recovery, and recrystallization. That is what we can see here in dynamic recrystallization. Here initially there is increasing stress requirement, then it becomes flat, this is a dynamic recovery phase, and then dynamic recrystallization comes into. Okay. This happens when the high temperature deformation is carried out. So, the mechanism of the dynamic recrystallization is concerned during the hot deformation, when metal is subjected to a critical strain value, the dynamic recrystallization occurs. So, a minimum level of the strain must be induced for dynamic recrystallization to start. In this case, the grain boundaries bulge locally and form the nuclei for the recrystallization. These nuclei grow by consuming the work hardened surrounding grains. So, here we can see initially we may have the work hardened material like this, then the new grains are formed selectively here at the boundaries. So, that will be the start of the recrystallization, and then the complete recrystallization takes place where fresh the new crystallographic free strain free the grains are formed. Now, here this is what has been explained in detail: work hardening, dynamic recovery and recrystallization. In the initial stage of the metal hard working, the increase in number of dislocations and interaction of dislocations causes the work hardening. So, that is the first stage, okay, and the effect of work hardening is much greater than the dynamic softening that is happening due to the recovery, and therefore the slope is positive like this, okay. The true stress presents the linear growth in the beginning, A to B say. As the hot deformation progresses, the accumulated energy in the material increases continuously with the continuous deformation, and this in turn facilitates the dynamic softening or dynamic recovery, okay, caused by the combination and recombination of the dislocations increases the rate of the increasing the rate of stress slowdown. So, here we can see it is slowing down stage, okay, where the material is still getting hardened, but at the slower rate, because dynamic recovery has started happening, but it is not as effective as that of the work hardening. Then we have, after attaining a particular critical stress state, if the dislocation density remains low for nucleation of the new grains, that is in the recrystallization that is needed, then the dynamic recrystallization does not occur. So, initially if the deformation is limited, dislocation density is less, then the dynamic recrystallization will not be happening, and in this situation true stress will remain unchanged after reaching the peak value. This means the dynamic recovery has occurred and true stress strain represents the dynamic recovery type. So, here after attaining this stage where we will see the work hardening effect is being balanced by the dynamic recovery and curve becomes flat. If the dislocation density is high enough for nucleation, then dynamic recrystallization will take place and the dynamic recrystallization mechanism will become active. An effect of the dynamic recrystallization will be causing significant softening. So, a drop in the curve due to the softening, and in this stage the softening will dominate over the work hardening effect. That is why our plot comes down, means the stress strain curve relationship becomes negative. Therefore, true stress will drop suddenly after reaching the peak value, and true stress strain diagram, this kind of the true stress strain diagram represents the dynamic recrystallization type. Now, you see the grain growth is the last stage after the recrystallization. If the high temperature is maintained for further longer time, then the increase in the size of the grains in the metal is observed at a high temperature, and this occurs after recovery and after recrystallization. These things are done, and still if the high temperature is maintained for longer time, then a recrystallized metal will show the growth of the grains. This is the normal growth of grain, where the grain growth of each grain has attained the larger size. But if the selectively few grains grow, but at the cost of other grains, then we have the abnormal grain growth. And why this happens? Because the further reduction in the internal energy can only be achieved by reducing the total grain boundary area, and that is why when the high temperature is maintained for longer time, grains grow. And how does it affect the metal itself? A metal heated above the recrystallization temperature for long experiences the grain growth, it is fine, and grains grow larger by atoms migrating from another grains that may eventually disappear. So, the grain growth occurs at the cost of all other smaller grains, and grain growth affects the mechanical properties, physical properties of the material such as hardness, strength and ductility. Therefore, controlling the grain growth is important because many metal properties depend on the grain size and its distribution. So, now I will summarize in this presentation. In this presentation, I have talked about the recovery, recrystallization and grain growth and the various factors that affect these important aspects related with the deformation of metal at a high temperature that has been covered. Thank you for your attention.